When scientists finally declassified what happened after the US military exploded nuclear bombs in space, they discovered something terrifying. The radiation is still there, circling Earth like an invisible death ring, and it's getting worse. In 2025, LEO now hosts almost 10,000 active satellites, up from under 50 in 1962. But what most people don't know is that we're sending them through zones where Starfish Prime and subsequent tests injected charged particles into Earth's Van Allen belts, creating persistent artificial radiation zones that lasted for 5 years. The tests transformed Earth's electromagnetic environment into an unforeseen hazard. This is the legacy of Operation Starfish Prime, and the consequences are finally catching up to us in ways nobody predicted back in 1962. The electromagnetic weapon that never should have existed. These high-altitude tests were designed to study electromagnetic pulse effects by using nuclear detonations as powerful energy sources. That was the first thing declassified documents revealed about America's space nuclear program. Military scientists weren't trying to blow things up in the traditional sense. They were building electromagnetic field generators that happened to use nuclear explosions as their power source. The entire concept flipped conventional warfare on its head because the destructive force wasn't the heat or the blast wave anymore. It was the invisible electromagnetic energy that radiated out from the detonation point at the speed of light. Cold War physicists had stumbled onto something unprecedented. They discovered they could turn Earth's protective magnetic field into a weapon delivery system by pumping artificial radiation into specific orbital zones. The process worked like hijacking a planetary defense mechanism and redirecting it against enemy targets. Nuclear explosions in space released massive quantities of charged particles that would get captured by Earth's magnetic field lines and then transported across vast distances to predetermined locations on the planet's surface. These weren't weapons in any traditional military sense. They were electromagnetic field manipulators capable of disabling entire continental regions without firing a single conventional shot. When Starfish Prime detonated 250 miles above the Pacific, its electromagnetic pulse overwhelmed scientific instruments and disabled electronics 1,400 kilometers away in Hawaii. The charged particles from a space nuclear detonation could follow magnetic field lines from one hemisphere to another, carrying their destructive electromagnetic energy across thousands of miles of empty space before delivering their payload to enemy territory. A single bomb exploded over the Indian Ocean could theoretically cripple Soviet electronic systems on the other side of the planet. Cold War planners saw potential for EMP tests to disable guidance electronics on ICBMs in flight, introducing defensive possibilities. Soviet ICBMs relied on electronic guidance systems to navigate from launch to target, and these systems were vulnerable to electromagnetic interference. A properly positioned electromagnetic field could turn incoming nuclear missiles into expensive pieces of scrap metal falling harmlessly into the ocean. The offensive applications were even more terrifying. Scientists calculated that electromagnetic pulses generated in space could reach across entire continents through magnetic field line connections. The electromagnetic energy would travel along these invisible highways in Earth's magnetic field and emerge anywhere the field lines intersected with the planet's surface. Enemy radar installations, communication networks, power grids, and military command centers could all be disabled simultaneously without warning and without the political complications of a traditional nuclear attack. The scope of electromagnetic effects operating through magnetic field lines exceeded anything military strategists had previously imagined. Unlike conventional weapons that affected only their immediate blast radius, space nuclear detonations could project their electromagnetic influence across multiple time zones. The charged particles would spiral along magnetic field lines at incredible speeds, creating sustained electromagnetic interference that could persist for hours or even days after the initial explosion. Military leaders found themselves experimenting with planetary-scale electromagnetic warfare that treated Earth's magnetic field as a weapon system. They weren't just testing individual bombs anymore. They were testing whether they could manipulate the electromagnetic environment of the entire planet to gain strategic advantage over the Soviet Union. The implications went far beyond traditional military thinking because success would mean controlling electromagnetic spectrum dominance across multiple continents simultaneously. The strategy seemed viable because electromagnetic weapons offered several advantages over conventional nuclear missiles. They could disable enemy capabilities without creating radioactive fallout on friendly territory. They operated at light speed, making them impossible to intercept or defend against using existing technology. They could target specific types of electronic systems while leaving others relatively unaffected. Most importantly, they could be deployed without the massive infrastructure requirements of traditional nuclear delivery systems. Scientists working on the program understood they were entering uncharted territory with potentially catastrophic consequences, but they couldn't predict what those consequences might be. The electromagnetic effects they were measuring in laboratory conditions were already exceeding their theoretical calculations. When they scaled up from small test explosions to multi-megaton space detonations, the results consistently surprised them with their intensity and duration. Each test revealed new electromagnetic phenomena that their existing scientific models couldn't explain or predict. The experimental nature of the program meant that scientists were learning about electromagnetic effects in real time during actual nuclear detonations. They had no way to predict how space-based electromagnetic pulses would interact with Earth's natural magnetic field over extended time periods. They didn't understand how artificial radiation would behave when injected into the planet's radiation belts. They couldn't calculate how long electromagnetic effects would persist after the initial explosion. Military planners pushed forward with testing because the potential strategic advantages outweighed the unknown risks. Electromagnetic warfare offered the possibility of decisive victory without mutual destruction. If the United States could perfect space-based electromagnetic weapons before the Soviet Union developed countermeasures, American military superiority would be virtually guaranteed. The electromagnetic effects could disable Soviet nuclear capabilities while leaving American systems protected through geographic positioning and electromagnetic shielding. The urgency of Cold War competition drove rapid advancement from theoretical concepts to actual nuclear testing in space. Scientists had identified the basic principles of electromagnetic warfare through magnetic field manipulation, but they needed real nuclear explosions to test whether their theories would work at the massive scales required for military effectiveness. Laboratory simulations couldn't replicate the electromagnetic intensity generated by multi-megaton thermonuclear detonations in the vacuum of space. Each successful test revealed that electromagnetic effects were more powerful and more persistent than anyone had predicted. The charged particles from nuclear explosions weren't dissipating into space as expected. Instead, they were getting trapped in Earth's magnetic field and creating artificial radiation zones that continued generating electromagnetic interference long after the original explosion. Scientists realized they weren't just creating temporary electromagnetic weapons anymore. They were permanently altering Earth's electromagnetic environment in ways that would affect all future space operations, and the key to understanding how lay in the planet's own magnetic field system. Earth's magnetic shield becomes a weapon. Military physicists realized they could turn Earth's core-driven magnetic field into a weapon delivery system by hijacking the planet's natural protective mechanisms. The magnetic field that shields us from deadly solar radiation could be repurposed to carry artificial radiation from nuclear explosions to any location on Earth. Scientists weren't just exploding bombs in space anymore. They were injecting charged particles into a planetary transport network that could deliver electromagnetic destruction anywhere the magnetic field lines touched the surface. Earth's magnetic field operates like an enormous three-dimensional highway system extending thousands of miles into space. The planet's core generates these invisible roadways through the movement of liquid iron in the outer core, which acts like a massive electrical generator. The magnetic field lines flow in continuous loops from the southern hemisphere to the northern hemisphere, creating Earth's core-driven magnetic field traps charged particles in concentric Van Allen belts, now known to include artificial belts from 1962 tests. These field lines reach far beyond the atmosphere into deep space, forming a protected bubble called the Magnetosphere that extends roughly 10 times the planet's diameter on the sunward side. The magnetic highway system works because charged particles from nuclear explosions follow these field lines like cars following roads. When scientists detonated nuclear weapons in space, the explosion released billions of highly energetic electrons and other charged particles. These particles couldn't travel in straight lines through the magnetic field. Instead, they got captured by the magnetic field lines and forced to spiral along the predetermined paths that connected different regions of the planet. The charged particles would travel at incredible speeds along these magnetic highways, carrying their electromagnetic energy from the explosion site to wherever the field lines intersected with Earth's surface. Military strategists discovered they could target specific locations on Earth by choosing the right detonation point in space. The magnetic field lines that passed through the Indian Ocean also passed through parts of the Soviet Union. This meant a nuclear explosion positioned correctly above the Indian Ocean would send charged particles racing along magnetic field lines directly into Soviet territory. The electromagnetic energy would travel thousands of miles through space along these invisible highways and emerge over Moscow, Leningrad, or any other city located along the same magnetic field line. Enemy electronics would be disabled by electromagnetic energy that originated from a bomb they never saw coming. The magnetic conjugate effect made this global targeting possible because magnetic field lines connect opposite hemispheres in predictable patterns. Scientists mapped these connections and discovered that every point in the northern hemisphere has a corresponding conjugate point in the southern hemisphere. Charged particles released at one conjugate point would automatically travel to the other conjugate point by following the connecting magnetic field line. This gave military planners the ability to attack any location on Earth by detonating a nuclear weapon at the corresponding conjugate point in international waters or friendly territory. Scientists plan to weaponize the same mechanisms that create the northern lights and southern lights. Aurora displays happen when charged particles from the sun get channeled down magnetic field lines and collide with atmospheric gases near the poles. Nuclear explosions in space would work exactly the same way, except the charged particles would be artificial and far more energetic than natural solar particles. Instead of creating beautiful light displays, the artificial charged particles would create devastating electromagnetic pulses when they reached the atmosphere. The concept of magnetic bottles offered even more precise targeting capabilities for space-based electromagnetic weapons. Certain configurations of magnetic field lines can trap charged particles in specific orbital zones and hold them there for extended periods. Scientists discovered they could create artificial radiation belts by injecting nuclear explosion debris into these magnetic bottle regions. The trapped particles would orbit Earth repeatedly while gradually leaking electromagnetic energy down to the surface. Researchers later found these belts persisted at destructive intensities for up to 5 years post-test. This created the possibility of sustained electromagnetic attacks that could continue for weeks or months after the initial nuclear detonation. Military planners understood that magnetic field manipulation would give them unprecedented strategic advantages over conventional nuclear weapons. Magnetic field weapons could strike targets on the opposite side of the planet without crossing international boundaries or violating airspace. They could disable enemy capabilities without creating radioactive fallout on friendly territory. They could target specific types of electronic systems while leaving others relatively unaffected. Most importantly, they operated at the speed of light, making them impossible to intercept or defend against using existing missile defense technology. Early theoretical calculations suggested that magnetic field effects might be more powerful than conventional nuclear weapon effects. The electromagnetic energy from a space nuclear explosion could travel much farther than heat or blast effects because magnetic field lines extended thousands of miles from the detonation point. This meant that a relatively small nuclear weapon exploded in the right location could potentially affect a much larger area than a much bigger nuclear weapon exploded on the ground. The magnetic field amplified and directed the electromagnetic effects in ways that concentrated the destructive energy over vast distances. Scientists expected magnetic effects to manifest in predictable ways based on their understanding of natural aurora phenomena and radiation belt behavior. They predicted that artificial charged particles would follow magnetic field lines just like natural solar particles. They calculated that electromagnetic energy would be deposited in the atmosphere at predictable conjugate locations. They estimated that the effects would dissipate over several days or weeks as the artificial charged particles gradually lost energy through collisions with atmospheric gases. Military urgency drove the progression from theoretical magnetic field weapons to actual nuclear testing in space. Cold War competition meant that American scientists needed to perfect electromagnetic warfare capabilities before Soviet scientists developed similar weapons or effective countermeasures. The strategic implications of magnetic field weapons were too significant to leave untested. But before they could attempt full-scale space detonations, military scientists needed to solve a fundamental engineering problem that would require some very unconventional thinking. Operation Hardtack's balloon bomb experiment. The challenge was getting nuclear weapons high enough to test electromagnetic effects without rockets powerful enough to reach true space altitudes. In 1958, hard-to-reach altitudes led to the Yucca balloon test, which proved high-altitude EMP can be 1,000 times stronger than ground tests. Military scientists strapped a 1.7 kiloton nuclear device to a weather balloon and floated it 85,000 feet above the Pacific Ocean. The image of America's most sophisticated weapon system dangling beneath a giant balloon captures the experimental desperation of early space nuclear testing. Operation Hardtack represented the military's first serious attempt to understand what nuclear weapons could do in the upper atmosphere. The balloon approach wasn't chosen because it was elegant or reliable. Scientists chose balloons because they had no other option for reaching the altitudes necessary to test electromagnetic pulse effects. Rockets in 1958 couldn't carry nuclear payloads to the heights required for true space testing, and aircraft couldn't fly high enough to simulate the electromagnetic conditions that military planners wanted to create above enemy territory. The experimental nature of balloon-delivered nuclear weapons becomes clear when you consider the preparation required. Military engineers conducted 76 practice balloon launches before they risked an actual nuclear device. Each practice launch tested different aspects of the balloon system, from payload delivery mechanisms to altitude control systems to detonation timing. The practice launches revealed numerous technical problems that had to be solved before anyone would trust a nuclear weapon to a weather balloon floating miles above the Pacific Ocean. Scientific uncertainty drove the extensive preparation because nobody knew what would happen when a nuclear weapon exploded at 85,000 feet. The altitude placed the detonation point above most of the atmosphere, but below the edge of space. Scientists weren't sure whether electromagnetic effects would behave like ground-level nuclear explosions or like the space-based explosions they were trying to simulate. The balloon test represented a critical proof of concept that would determine whether high-altitude electromagnetic weapons were worth pursuing with more expensive rocket delivery systems. The Yucca test launched from a U.S. aircraft carrier positioned off the coast of Bikini Atoll on April 28, 1958. The balloon carried its nuclear payload slowly upward through the atmosphere while scientists monitored its ascent from ships positioned at safe distances around the test zone. The gradual ascent gave scientific teams time to conduct final equipment checks and position their measurement instruments, but it also created hours of mounting tension as the balloon drifted higher toward the predetermined detonation altitude. Weather conditions added uncertainty to an already experimental process. High-altitude winds could push the balloon off course, potentially placing the nuclear explosion over inhabited areas instead of empty ocean. The balloon's ascent rate depended on atmospheric pressure and temperature variations that couldn't be predicted with complete accuracy. Scientists had to constantly adjust their calculations as the balloon climbed through different atmospheric layers, each with its own wind patterns and thermal characteristics. The detonation itself occurred at exactly 85,000 feet above sea level, placing the nuclear explosion in the stratosphere, where the atmosphere is thin enough to allow electromagnetic effects to propagate with minimal interference. The 1.7 kiloton yield was relatively small compared to strategic nuclear weapons, but scientists weren't testing the explosive power. They were measuring the electromagnetic pulse intensity generated by nuclear fission in the upper atmosphere. The electromagnetic measurements would determine whether high-altitude nuclear explosions could create the electromagnetic warfare effects that military strategists were hoping to achieve. Scientific instruments positioned throughout the Pacific region detected electromagnetic effects that exceeded all theoretical predictions. The high-altitude electromagnetic pulse was over 1,000 times more intense than equivalent ground-level explosions. This single measurement revolutionized military thinking about electromagnetic warfare because it proved that altitude amplified electromagnetic effects far beyond anything scientists had calculated using existing theoretical models. The electromagnetic pulse propagated through the thin upper atmosphere with almost no attenuation, creating electromagnetic field strengths that would be impossible to achieve with ground-based nuclear weapons. The intensity differential changed everything. Military planners thought they understood about nuclear weapon applications. Ground-level nuclear explosions dissipate most of their electromagnetic energy through interactions with dense atmospheric gases and surface materials. High-altitude explosions face much less atmospheric resistance, allowing electromagnetic energy to propagate over vast distances without significant attenuation. The balloon test proved that a relatively small nuclear weapon exploded at high altitude could create electromagnetic effects comparable to much larger weapons exploded at ground level. Military leadership immediately recognized they had stumbled onto a weapon system far more powerful than conventional nuclear applications. The electromagnetic effects measured during Yucca suggested that high-altitude nuclear explosions could disable electronic systems across entire regions without creating the radioactive fallout associated with ground-level nuclear attacks. The strategic implications were enormous because electromagnetic weapons offered military advantages that conventional nuclear weapons couldn't provide. The discovery accelerated the urgency of space nuclear testing programs throughout the military establishment. Scientists realized they needed to test electromagnetic effects at even higher altitudes to determine the maximum potential of space-based electromagnetic weapons. The balloon test had proved the basic concept, but true space altitudes might produce electromagnetic effects that were orders of magnitude more powerful than the already impressive results from 85,000 feet. The electromagnetic intensity measurements from Yucca also revealed that scientists had been dramatically underestimating the power of space-based electromagnetic weapons. Theoretical calculations based on ground-level nuclear testing had failed to account for the electromagnetic amplification effects that occurred in the upper atmosphere and space. The balloon test proved electromagnetic weapons could be far more destructive than anyone had predicted, which meant that space nuclear testing needed to proceed more carefully to avoid accidentally creating electromagnetic effects that exceeded safe levels. The success of Yucca guaranteed that more powerful tests would follow as military planners pushed toward true space nuclear testing. But first, they needed rockets capable of carrying much larger nuclear payloads to much higher altitudes. The next test would escalate beyond anything they had attempted before, using a multi-megaton warhead that would create effects visible across the entire Pacific region. When Teak created a second Sunday, Teak's 3.8 megaton warhead over Johnston Island lit the sky like a second sun visible from Hawaii, an unplanned detonation above the island that demonstrated space nuclear weapons could create effects far beyond anything military planners had anticipated. The artificial daylight hung in the atmosphere for 30 minutes, while observers watched in horror from hundreds of miles away. And the thermal radiation was intense enough to give sunburns to servicemen stationed on Johnston Island who happened to be looking in the wrong direction when it happened. The Teak test represented a massive escalation from the balloon experiments that had proved high-altitude electromagnetic weapons were viable. Military engineers had moved from floating 1.7 kiloton devices on weather balloons to launching a 3.8 megaton thermonuclear warhead on top of a Redstone missile. The Redstone was America's most reliable rocket system at the time, originally designed to deliver nuclear warheads to Soviet targets during actual warfare. Using it for space nuclear testing meant that scientists were finally working with delivery systems and warhead yields that matched real military applications. Johnston Atoll provided the perfect launch site for testing weapons that might create effects visible across multiple time zones. The remote Pacific location sat roughly 800 miles southwest of Hawaii, in what military planners described as the exact middle of nowhere. The isolation meant that even catastrophic test failures wouldn't endanger civilian populations, and the vast ocean surrounding the atoll could absorb whatever electromagnetic or thermal effects the nuclear explosion might produce. Johnston Atoll had been specifically chosen as a nuclear testing facility because it was far enough from everything else to contain disasters. the Redstone missile carried its thermonuclear payload upward through the atmosphere, exactly as designed, but the guidance system malfunctioned just before the predetermined detonation point. Instead of exploding over empty ocean at a safe distance from the launch site, the 3.8 megaton warhead detonated directly above Johnston Island. The guidance failure meant that military personnel on the ground experienced the full effects of a space nuclear explosion from just a few miles away, essentially turning the test site into ground zero for electromagnetic and thermal effects that were supposed to impact only remote ocean areas. The visual spectacle of a nuclear explosion in the upper atmosphere defies normal description because nothing in human experience prepares you for seeing an artificial sun appear in the sky. Ground-level nuclear explosions create the familiar mushroom cloud as hot gases rise through dense atmospheric layers, but space nuclear explosions look completely different. The 3.8 megaton warhead created an expanding sphere of incandescent plasma that glowed like a miniature star suspended in the thin upper atmosphere. The plasma sphere was bright enough to illuminate the entire Pacific region with artificial daylight. The artificial sun remained visible for approximately 30 minutes as the hot plasma gradually cooled and dispersed through the upper atmosphere. During those 30 minutes, anyone looking toward Johnston Atoll from hundreds of miles away could see a new light source that rivaled the actual sun in brightness and intensity. The prolonged visibility demonstrated that space nuclear explosions created thermal effects that persisted far longer than ground-level explosions, where the fireball dissipates within seconds after detonation. Thermal radiation from the artificial sun was intense enough to cause immediate physical harm to military personnel stationed on Johnston Island. The thermal intensity exceeded anything that ground-level nuclear testing had produced because the explosion occurred above most of the atmosphere, allowing thermal radiation to propagate without atmospheric absorption. Military medical personnel had to treat radiation burns caused by an artificial sun that shouldn't have existed. The electromagnetic effects proved even more devastating than the thermal radiation because they affected electronic systems across the entire Pacific region. The explosion created electromagnetic pulses that propagated through the atmosphere and along magnetic field lines, disrupting high-frequency communications across thousands of miles of ocean. High-frequency communications across the Pacific were out for 8 hours as electromagnetic energy from the space nuclear explosion overwhelmed electronic equipment far from the test site. Military leaders realized they had accidentally created a weapons system far more powerful than conventional nuclear applications could provide. The Teak test proved that space nuclear explosions could affect targets thousands of miles away from the detonation point through electromagnetic and thermal effects that traveled at the speed of light. A single space-based nuclear weapon could potentially disable enemy communications, navigation, and electronic systems across multiple countries simultaneously without creating the radioactive fallout associated with ground-level nuclear attacks. The global reach of electromagnetic weapons became clear as scientists analyzed the full extent of the tech test effects. Electromagnetic pulses had propagated along magnetic field lines to reach locations in both hemispheres, confirming that space nuclear explosions could target any location on Earth by following predetermined magnetic pathways. The test demonstrated that electromagnetic warfare offered strategic capabilities that conventional nuclear weapons couldn't match because electromagnetic effects could cross international boundaries without violating airspace or territorial sovereignty. Scientific measurements revealed that the electromagnetic and thermal effects were far more intense than theoretical calculations had predicted. Computer models based on ground-level nuclear testing had failed to account for the amplification effects that occurred when nuclear explosions happened above the dense atmosphere. The vacuum-like conditions at high altitude allowed electromagnetic and thermal energy to propagate with minimal attenuation, creating effects that were orders of magnitude more powerful than equivalent ground-level explosions. The unexpected intensity of the Tiki test's effects prompted immediate concerns about what might happen if military planners proceeded with even more powerful space nuclear testing. The 3.8 megaton Tiki explosion had created electromagnetic chaos across the Pacific region, but scientists were already planning tests with much larger warheads at even higher altitudes. The electromagnetic effects scaled exponentially with both warhead yield and detonation altitude, which meant that true space nuclear explosions might. create electromagnetic pulses powerful enough to affect global electronic infrastructure. The success of TEAC guaranteed that more ambitious testing would follow, but the timing of these experiments would coincide with the most dangerous period of the Cold War. As 1962 approached, the world was moving toward a nuclear confrontation that would bring both superpowers to the brink of global war, and space-based electromagnetic weapons were about to become part of
Operation
that terrifying
Fishbowl
equation.
launched during 1962, the same year as the Cuban Missile Crisis, underscoring the extreme tensions that defined Cold War nuclear competition. While President Kennedy and Premier Khrushchev faced off over Soviet nuclear missiles in Cuba, American scientists were simultaneously conducting their most ambitious space nuclear testing program just 90 miles above Earth's surface. The convergence of nuclear brinksmanship and experimental weapons testing created a period when the world balanced on the edge of nuclear war, while military planners pushed electromagnetic warfare capabilities into uncharted territory. Both the Cuban Missile deployment and the American space nuclear testing program emerged from the same strategic logic that dominated Cold War military planning. Nuclear deterrence theory required both superpowers to demonstrate increasingly sophisticated nuclear capabilities to maintain credible threats against enemy first strike scenarios. The Soviet Union was placing medium-range ballistic missiles in Cuba to counter American nuclear superiority, while the United States was exploding nuclear weapons in space to develop electromagnetic warfare capabilities that could disable Soviet missile systems during flight. Space nuclear testing became integrated into broader nuclear deterrence strategy because electromagnetic weapons offered unique advantages over conventional nuclear missiles. Traditional nuclear deterrence relied on the threat of mutual destruction through ground-based nuclear attacks, but space-based electromagnetic weapons could potentially disable enemy nuclear capabilities without triggering full-scale nuclear retaliation. Military strategists recognized that electromagnetic warfare might provide a way to achieve nuclear superiority without crossing the threshold into mutual annihilation that made conventional nuclear war too dangerous to contemplate. Military logic during this period centered on the concept of first strike advantage and the elimination of second strike capabilities. If the United States could perfect electromagnetic weapons that disabled Soviet nuclear missiles during their flight path through space, American nuclear forces could potentially survive a Soviet first strike while preventing Soviet forces from surviving an American first strike. Space nuclear testing was designed to determine whether electromagnetic weapons could tip the strategic balance decisively in favor of whichever superpower mastered the technology first. The proximity to actual nuclear conflict made space nuclear testing exponentially more dangerous because experimental weapons might have been pressed into service during the Cuban crisis if diplomatic solutions had failed. American military planners were developing electromagnetic warfare capabilities that remained largely untested, but they were doing so while facing the real possibility that nuclear war might begin within days or weeks. The pressure to accelerate testing schedules and deploy experimental weapons systems created scenarios where inadequately tested technologies might have been used in actual conflict situations. Scientists working on space nuclear testing faced unprecedented pressure to advance electromagnetic warfare capabilities rapidly during the Cuban crisis period. Normal scientific protocols for testing and validation were compressed into emergency timelines as military leadership demanded immediate answers about electromagnetic weapon effectiveness. Research teams had to conduct nuclear testing while simultaneously preparing for the possibility that their experimental weapons might be needed for actual military operations against Soviet targets within a matter of weeks. The Cuban Missile Crisis demonstrated how quickly Cold War tensions could escalate from diplomatic posturing to nuclear brinksmanship, which added urgency to space nuclear testing programs that were already operating under compressed timelines. Military planners realized that electromagnetic weapons could provide crucial advantages during nuclear crises by offering options between conventional military responses and full nuclear war. Space-based electromagnetic weapons could disable enemy capabilities without creating the massive casualties and radioactive devastation that made nuclear war politically and strategically unacceptable. International implications of space nuclear testing during the Cuban crisis extended far beyond bilateral Soviet-American competition, because electromagnetic weapons could affect global electronic infrastructure simultaneously. Unlike conventional nuclear weapons that created localized destruction, space-based electromagnetic weapons could disable communications, navigation, and power systems across multiple countries without regard for political boundaries. The development of such weapons during a period of maximum international tension raised the possibility that nuclear crisis escalation might involve neutral countries suffering electromagnetic attacks without warning. Military planners faced the terrifying possibility that space nuclear weapons might be deployed operationally if the Cuban crisis escalated beyond diplomatic resolution. Electromagnetic weapons were still experimental and largely untested, but they offered the only potential solution to Soviet missile threats that didn't require full-scale nuclear retaliation. The decision-making process during nuclear crises operates under extreme time pressure, which meant that experimental weapons systems might be pressed into service before their effects were fully understood or their reliability was adequately verified. The convergence of experimental weapons testing and nuclear crisis created scenarios where untested technologies might have been used against Soviet targets with unpredictable consequences. Scientists conducting space nuclear tests understood that their research might transition from laboratory experimentation to actual weapons deployment within days or weeks if diplomatic solutions to the Cuban crisis failed. The electromagnetic effects they were measuring in controlled test conditions might soon be unleashed against enemy targets under combat conditions where precise control and measurement would be impossible. Electromagnetic warfare superiority offered the possibility of decisive victory in nuclear conflict without the mutual destruction that made conventional nuclear strategy so dangerous. Whichever superpower gained the ability to disable enemy nuclear systems through space-based electromagnetic attacks could potentially win a nuclear war without suffering comparable retaliation. This strategic advantage was significant enough to justify accelerated testing programs, despite the obvious risks of conducting nuclear experiments during periods of maximum international tension. The pressure to perfect electromagnetic weapons during the Cuban crisis period meant that scientists were pushing the boundaries of nuclear testing into uncharted territory where the consequences of miscalculation could extend far beyond the immediate test objectives. Space nuclear explosions were creating electromagnetic effects that exceeded theoretical predictions, but military urgency prevented the careful analysis that would normally precede escalation to more powerful tests. Scientists were learning about electromagnetic warfare through real nuclear explosions while facing the possibility that their experimental weapons might be needed for actual military operations. The most ambitious test of this dangerous period was scheduled to demonstrate whether electromagnetic weapons could provide the decisive military advantages that Cold War strategy demanded. The largest nuclear weapon ever planned for space detonation would either prove that electromagnetic warfare offered revolutionary strategic capabilities or reveal consequences too dangerous to continue. Starfish Prime's catastrophic success. At exactly 11 p.m. Greenwich Mean Time on July 9, 1962, a 1.4 megaton thermonuclear warhead exploded 400 kilometers above the Pacific Ocean in what would become the most consequential nuclear test in human history. The Thor rocket had carried its payload to an altitude where the International Space Station orbits today, placing the explosion directly in the path of future satellite constellations that didn't exist yet. Scientists had finally achieved their goal of detonating the largest nuclear weapon ever exploded in space, but they were about to discover that success could be more terrifying than failure. The explosion overwhelmed every scientific instrument positioned to measure its effects. EMP amplitude exceeded measurement limits on all sensors as radiation detectors designed to handle the most extreme nuclear testing scenarios simply maxed out their readings and stopped functioning. Electromagnetic sensors built specifically for space. Nuclear testing couldn't register the full intensity of the pulse because the energy levels exceeded anything scientists had prepared for. The monitoring equipment failures meant that researchers were measuring the most important nuclear test in history with instruments that couldn't actually measure what was happening. Space nuclear explosions look nothing like the nuclear detonations that people expect to see. There was no mushroom cloud because there wasn't enough atmosphere to create one. Instead, the warhead released its energy as pure electromagnetic radiation that expanded outward in perfect spheres of deadly light. Gamma rays and X-rays radiated from the explosion point at the speed of light, creating an intensely bright flash that illuminated the entire region around Johnston Atoll. The visual spectacle was unlike anything human beings had ever witnessed because space nuclear explosions operate according to completely different physics than ground-level detonations, without dense atmospheric gases to absorb and redirect the energy. The nuclear explosion expanded as pure radiation and charged particles moving outward from the detonation point. The spherical expansion created a temporary artificial star suspended 400 kilometers above Earth, visible to anyone looking in the right direction across thousands of miles of the Pacific Ocean. The electromagnetic pulse generated by Starfish Prime proved to be orders of magnitude more powerful than scientific predictions had suggested. The EMP traveled at light speed through the thin upper atmosphere and along magnetic field lines, carrying electromagnetic energy far beyond the visual effects of the explosion itself. Scientists had calculated electromagnetic pulse effects based on previous high-altitude testing, but the combination of the 1.4 megaton yield and the 400-kilometer altitude created electromagnetic field strengths that exceeded all existing theoretical models. Hawaiian Islands sat 900 miles away from the detonation point, but the electromagnetic effects reached them within milliseconds of the explosion. Approximately 300 streetlights failed simultaneously across Honolulu as the electromagnetic pulse overwhelmed the electrical systems that controlled urban lighting infrastructure. Burglar alarms throughout the Hawaiian Islands triggered spontaneously as electromagnetic energy interfered with the electronic sensors and control circuits that operated security systems. Telephone communications experienced widespread disruptions as electromagnetic interference damaged switching equipment and transmission lines throughout the island chain. The electromagnetic effects in Hawaii demonstrated that space nuclear weapons could disable electronic infrastructure across distances that conventional weapons could never reach. The 900-mile separation between Johnston Atoll and the Hawaiian Islands was roughly equivalent to the distance between major American cities, which meant that space nuclear weapons could potentially affect multiple states simultaneously from a single detonation point. Military planners realized they had created a weapon system capable of disabling enemy electronics across entire regions without causing the physical destruction associated with conventional nuclear attacks. Artificial auroras appeared in both hemispheres exactly as scientists had predicted based on magnetic field theory. The northern aurora manifested in the sky above the detonation area as charged particles from the nuclear explosion interacted with atmospheric gases along magnetic field lines. Simultaneously, a southern aurora appeared over the Samoan Islands as the same charged particles followed magnetic field lines to their conjugate point in the opposite hemisphere. The dual aurora phenomenon proved that nuclear explosions in space could deliver electromagnetic effects to any location on Earth by following predetermined magnetic pathways. The magnetic field weapon theory was finally confirmed through direct observation as charged particles from the Starfish Prime explosion traveled thousands of miles along invisible magnetic highways to emerge in the southern hemisphere. Scientists could now verify that space nuclear weapons offered global targeting capabilities that conventional nuclear weapons couldn't provide. A single nuclear explosion positioned correctly in space could affect multiple continents simultaneously by injecting charged particles into magnetic field lines that connected opposite sides of the planet. High-energy electrons from the nuclear explosion became trapped in Earth's magnetic field instead of dissipating into space as scientists had expected. The magnetic field lines that normally protected Earth from solar radiation were now trapping artificial radiation from the nuclear explosion, creating an artificial radiation belt that encircled the planet at the altitude where the explosion had occurred. The intensity of electrons in low Earth orbit increased by several orders of magnitude as the artificial radiation accumulated in the magnetic field geometry surrounding the detonation altitude. The trapped electrons created a permanent artificial radiation belt that posed immediate threats to satellite operations and future space missions. Scientists realized they had accidentally created a zone of artificial radiation that would persist far longer than the temporary electromagnetic effects they had been trying to measure. The artificial radiation belt represented a fundamental alteration to Earth's space environment that would affect all future satellite deployments and space exploration missions. Satellite failures began within days of the Starfish Prime detonation as artificial radiation slowly destroyed the electronic systems of spacecraft operating in the affected orbital zones. 3 satellites stopped functioning within the first week after the explosion as radiation damage accumulated in their electronic components and solar panels. 6 additional satellites failed over the following months as the artificial radiation belt continued to damage spacecraft operating in low Earth orbit. The radiation effects proved to be cumulative and persistent rather than immediate and temporary as scientists had predicted. Military planners had achieved their goal of demonstrating electromagnetic warfare capabilities, but they had also created something unexpected that would challenge every assumption about how long nuclear effects should last in space. The radiation ring that won't go away. Scientists expected the artificial radiation from Starfish Prime to fade away within a few weeks, maybe a few months at most. That's not what happened. The high-energy electrons from the 1962 nuclear explosion remained trapped in Earth's magnetic field for up to 5 years, creating a permanent artificial radiation belt that encircled the planet like an invisible ring of death. In 1968, studies reported artificial electrons lingered for up to 5 years, still damaging satellites, still creating hazards for space missions, still proving that nuclear explosions in space created consequences that nobody had predicted or planned for. The persistence of artificial radiation completely overturned scientific understanding of how space nuclear explosions would behave. Theoretical models suggested that charged particles from nuclear detonations would gradually lose energy through interactions with the thin upper atmosphere and eventually dissipate into space. Instead, Earth's magnetic field was acting like a giant storage container, trapping the artificial electrons in specific orbital zones where they could spiral around the planet indefinitely. The magnetic field geometry that normally protected Earth from solar radiation was now holding artificial radiation in place for years instead of allowing it to escape. High-energy electrons from the nuclear explosion became concentrated in orbital zones between roughly 400 and 4,000 kilometers above Earth's surface. These altitudes correspond exactly to the orbital paths used by most satellites and space missions, which meant that the artificial radiation belt was positioned to affect virtually all space-based infrastructure. The electron concentration in these zones increased by several orders of magnitude above natural background levels, creating radiation environments that were thousands of times more intense than anything spacecraft had been designed to handle. Earth's radiation environment had been permanently altered in ways that would affect space operations for the remainder of the decade. Natural radiation belts around Earth had taken millions of years to form through gradual accumulation of charged particles from solar wind and cosmic rays. Starfish Prime had created an artificial radiation belt of comparable intensity in a matter of minutes, then sustained it for years through magnetic field trapping mechanisms that scientists were still trying to understand. The artificial belt represented a fundamental change to the space environment that would complicate all future space exploration efforts. 9 satellites were disabled over months following the test as artificial radiation slowly destroyed electronic systems that had been designed to operate in the natural space environment. The failures weren't immediate catastrophic breakdowns, but gradual degradation as artificial radiation slowly wore down spacecraft components that couldn't handle the intense electron bombardment. The satellite destruction process worked like a slow-motion electromagnetic attack that continued long after the original nuclear explosion. High-energy electrons in the artificial radiation belt would collide with satellite components thousands of times per second, gradually breaking down the molecular structure of semiconductor materials and degrading the efficiency of solar power systems. Electronic circuits designed to operate for years in the natural space environment would fail within months when exposed to the artificial radiation created by Starfish Prime. Solar panels proved particularly vulnerable to artificial radiation because high-energy electrons degraded the photovoltaic cells that converted sunlight into electrical power. Satellites operating in the artificial radiation belt experienced steady declines in power generation capability as electron bombardment reduced the efficiency of their solar panels. Some spacecraft lost enough electrical power to shut down their communication systems, leaving them as expensive pieces of space debris orbiting through the radiation zone that had destroyed them. Artificial radiation interacted with natural radiation belts in ways that created even more complex and dangerous zones around Earth. The Van Allen radiation belts had been discovered just a few years before Starfish Prime, and scientists were still learning how natural radiation behaved in Earth's magnetic field. The artificial electrons from the nuclear explosion mixed with natural radiation to create hybrid zones where radiation levels fluctuated unpredictably. Some orbital altitudes that had been relatively safe for spacecraft became radiation hazards as artificial and natural electrons combined to produce radiation environments more intense than either source alone. The emerging space age faced radiation hazards that hadn't existed before 1962. Forcing space agencies to redesign satellites and modify mission planning procedures to account for artificial radiation effects. Communication satellites needed additional radiation shielding to protect their electronic systems from artificial electron bombardment. Navigation satellites required backup systems to maintain functionality if their primary electronics failed due to radiation damage. Weather monitoring satellites had to be repositioned to orbital altitudes that avoided the most intense artificial radiation zones. Space mission planning became exponentially more complicated as scientists struggled to map the artificial radiation zones and predict their long-term behavior. Manned space missions like the Gemini and Apollo programs had to account for radiation exposure levels that included artificial electrons in addition to natural space radiation. Astronauts faced higher radiation doses during missions that passed through artificial radiation belts, requiring modified flight paths and enhanced radiation protection systems. The implications for future space exploration extended far beyond the immediate satellite failures because artificial radiation represented a permanent alteration to the space environment. Every space mission launched after 1962 had to contend with radiation hazards that didn't exist before nuclear testing began. The artificial radiation belt created by Starfish Prime would affect spacecraft design, mission planning, and orbital mechanics for years after the original explosion. Scientific predictions about artificial radiation persistence had failed catastrophically because theoretical models couldn't account for the complex interactions between nuclear explosion debris and Earth's magnetic field. Computer simulations based on laboratory experiments had suggested that artificial radiation would dissipate within weeks or months, but the actual measurements showed radiation persisting for years. The magnetic field trapping mechanisms that sustained artificial radiation belts operated according to physics that weren't fully understood when the nuclear testing program began. Current space operations still deal with the legacy of artificial radiation from 1960s nuclear testing, though most of the original Starfish Prime electrons have finally dissipated after more than 60 years. Space agencies monitor radiation levels in orbital zones where artificial radiation belts once existed, and satellite designers continue to account for the possibility of similar artificial radiation events in their spacecraft protection systems. The space environment that exists today was shaped by decisions made during the most dangerous period of the Cold War, and those consequences continue to influence how we operate in the orbital zones. 2025's satellite swarms means 1962's legacy. Today, LEO hosts nearly 10,000 satellites, up from under 50 in 1962, creating a complex network of communication, navigation, weather monitoring, and internet service satellites that forms the backbone of modern civilization. The orbital zones, where 1960s nuclear testing created artificial radiation belts, are now crowded with thousands of satellites worth hundreds of billions of dollars. The empty space that military planners used for nuclear experiments has become the most valuable real estate in the solar system. The satellite launch rate has exploded since 2020 as commercial space companies have transformed orbital deployment from government-controlled operations to routine business activities. SpaceX alone has placed over 6,000 Starlink satellites in orbit to provide global internet coverage, with plans to expand the constellation to over 40,000 spacecraft. Amazon's Project Kuiper aims to deploy another 3,200 satellites for competing internet services. OneWeb, Telesat, and dozens of other companies are launching their own satellite constellations to capture shares of the growing space-based communications market. The orbital environment that once held a handful of experimental spacecraft now hosts multiple competing commercial networks operating simultaneously. Modern satellites operate in precisely the same orbital altitudes where Starfish Prime created its artificial radiation belt between 400 and 4,000 kilometers above Earth's surface. Low Earth orbit has become a crowded highway where Starlink satellites maintain internet connectivity. GPS satellites provide navigation services, and communication satellites relay phone calls and data transmissions around the globe. These orbital zones experience residual radiation effects from 1960s nuclear testing that have diminished over 6 decades but haven't completely disappeared. Space agencies continue monitoring radiation levels in these altitudes to ensure that artificial radiation doesn't pose ongoing threats to modern spacecraft. Starlink satellites navigate through space where artificial radiation once disabled satellites throughout the 1960s, but modern spacecraft incorporate radiation protection systems that didn't exist during the early space age. Modern satellites use radiation hardening techniques developed post-Starfish Prime, including radiation-hardened electronics designed to operate in harsh space environments where natural and artificial radiation can damage sensitive components. Solar panels feature protective coatings that resist radiation degradation. Electronic circuits include redundant systems that maintain functionality even if primary components fail due to radiation exposure. GPS satellites face particular challenges from space radiation because their orbital altitudes place them directly in natural radiation belts that surround Earth. The Global Positioning System operates approximately 20,000 kilometers above the surface in orbital zones where natural radiation is more intense than the low Earth orbit regions where most communication satellites operate. GPS spacecraft must withstand continuous radiation bombardment throughout their operational lifetimes while maintaining the precise timing accuracy required for navigation services. Any radiation-induced failures in GPS satellites would affect millions of users who depend on satellite navigation for transportation, agriculture, emergency services, and military operations. The electronic systems deployed in 2025 satellites are simultaneously more vulnerable and more protected than 1960s technology. Modern semiconductors use smaller transistors and lower operating voltages that make them more susceptible to radiation-induced errors and component failures. A single high-energy particle can corrupt data or damage circuits in ways that would have minimal effect on the larger, more robust electronics used in early satellites. However, contemporary spacecraft incorporate sophisticated radiation protection strategies including error correction codes, redundant processing systems, and automatic reset capabilities that allow satellites to recover from radiation-induced malfunctions. Commercial satellite operators account for radiation exposure when designing spacecraft and planning orbital operations, but they face economic pressures to minimize protection systems that add weight and cost to satellite deployments. Starlink satellites use mass production techniques that reduce individual spacecraft costs but limit the radiation protection that can be incorporated into each satellite. The constellation approach compensates for individual satellite vulnerabilities by deploying thousands of spacecraft so that radiation-induced failures don't significantly impact overall network performance. If artificial radiation disabled dozens of Starlink satellites simultaneously, the remaining spacecraft would maintain internet connectivity while replacement satellites are launched. Space debris problems in 2025 include remnants from satellites that failed during the 1960s due to artificial radiation from nuclear testing. Some spacecraft disabled by Starfish Prime's radiation belt continue orbiting Earth as space junk that poses collision hazards for modern satellites. The Kessler Syndrome describes how space debris creates cascading collision risks that could make orbital zones unusable for future space missions. Artificial radiation from nuclear testing contributed to the space debris problem by disabling satellites that became uncontrolled objects drifting through orbital space. Space agencies coordinate international efforts to prevent accidental electromagnetic interference that could replicate the effects of 1960s nuclear testing without using actual nuclear weapons. Solar storms create natural electromagnetic pulses that can disable satellites and disrupt communication networks in ways similar to artificial electromagnetic effects from nuclear explosions. Space weather monitoring systems track solar activity to predict when electromagnetic storms might affect satellite operations. Ground control stations prepare for communication blackouts and satellite malfunctions during severe space weather events that demonstrate how electromagnetic effects can impact modern space infrastructure. Modern space operations depend on orbital zones that would become completely unusable if nuclear testing resumed at 1960s levels. The International Space Station orbits at 400 kilometers altitude, directly in the zone where Starfish Prime created its most intense artificial radiation belt. Commercial crew missions carrying astronauts to the space station would face radiation exposure levels that could endanger human health if artificial radiation returned to 1960s intensity levels. Satellite internet services would fail across multiple orbital altitudes as radiation disabled thousands of spacecraft simultaneously. GPS navigation would become unreliable as radiation damaged the satellite constellation that provides positioning services for civilian and military users worldwide. The transformation of space from an empty testing ground to a crowded commercial highway means that any repeat of 1960s nuclear testing would face a fundamentally different target environment. Instead of disabling a handful of experimental satellites, a modern space nuclear explosion would encounter thousands of sophisticated spacecraft, operating critical infrastructure that billions of people depend on daily. The stakes have increased exponentially since 1962, but the physics of nuclear explosions in space remain exactly the same. The Kessler Syndrome nuclear nightmare. A nuclear weapon exploding in space today would create the ultimate catastrophe scenario for modern civilization. Picture this: a single electromagnetic pulse simultaneously disabling 8,000 active satellites instead of the handful that existed in 1962. Within seconds, every piece of space-based infrastructure that keeps our world running would go dark. But that's just the beginning of the nightmare. Those thousands of disabled satellites would become uncontrolled projectiles hurtling through orbital space at 17,000 miles per hour, setting off a chain reaction that could make space unusable for generations. The electromagnetic pulse from a modern space nuclear detonation would work exactly like Starfish Prime, except the target environment has fundamentally changed. In 1962, scientists disabled 3 satellites and considered it a significant result. Today, the same electromagnetic effects would simultaneously knock out thousands of Starlink internet satellites, dozens of GPS navigation satellites, hundreds of communication relay satellites, and countless weather monitoring spacecraft. The electromagnetic energy would propagate through orbital space at light speed, overwhelming the electronic systems of every satellite within the affected radiation zones before ground controllers could even register what was happening. Disabled satellites become massive space projectiles that follow ballistic trajectories with no ability to maneuver or avoid collisions. Modern satellites aren't designed to survive impacts from other spacecraft because orbital collisions were virtually impossible when only a few satellites existed in the 1960s. A dead Starlink satellite weighing 500 pounds and traveling at orbital velocity carries kinetic energy equivalent to a small explosive device. When thousands of these disabled spacecraft begin drifting through crowded orbital zones, they create collision scenarios that didn't exist during the early space age. Kessler warned in 1978 that debris collisions could cascade exponentially in crowded orbits. The Kessler Syndrome describes exactly what happens when space debris reaches critical density levels that trigger cascading destruction throughout orbital zones. Collisions between objects create more space debris, which increases the likelihood of additional collisions in an exponential progression that becomes impossible to stop once it begins. Each collision generates hundreds or thousands of smaller debris fragments that travel at orbital velocities and threaten every other spacecraft in the same altitude range. The debris field grows exponentially as each new collision adds more projectiles to an already overcrowded orbital environment. Orbital collision speeds make even tiny debris fragments incredibly destructive because spacecraft encounter debris at combined velocities exceeding 15,000 miles per hour. A paint fleck traveling at orbital velocity can puncture satellite solar panels. A bolt or screw can disable electronic systems through kinetic impact. Larger debris pieces can completely destroy operational satellites and create thousands of additional fragments that perpetuate the collision cascade. The debris creation process accelerates as more satellites are destroyed because each collision multiplies the number of dangerous objects in orbital space. Complete orbital infrastructure collapse becomes inevitable once the debris cascade reaches the point where operational satellites cannot avoid collision with disabled spacecraft and debris fragments. Low Earth orbit would transform from a carefully managed highway system into a shooting gallery where functional satellites face constant bombardment from debris created by previous collisions. Space agencies would be forced to abandon orbital zones that took decades to develop and billions of dollars to populate with operational spacecraft. The entire orbital environment between 200 and 2,000 kilometers altitude could become permanently unusable for satellite operations. Modern civilization depends on satellite infrastructure in ways that make orbital collapse catastrophically more destructive than anything possible in 1962. GPS navigation systems guide everything from commercial aviation to precision agriculture to emergency response services. Communication satellites relay phone calls, internet traffic, and financial transactions across continents. Weather satellites provide the data necessary for storm forecasting and climate monitoring. Military satellites coordinate defense operations and intelligence gathering. The simultaneous failure of these systems would affect every aspect of modern life within hours of the initial space nuclear detonation. Global economic systems would experience immediate collapse as satellite-dependent services failed simultaneously across multiple industries. Financial markets rely on satellite communication links to process trades and transfer funds between international banking systems. Supply chain logistics depend on GPS tracking to coordinate shipping and delivery operations. Credit card processing requires satellite connections to authorize transactions and prevent fraud. The economic disruption would cascade through interconnected systems as businesses lost the ability to communicate with customers, process payments, or coordinate operations across geographic distances. Communication system failures would isolate entire regions from global networks that depend on satellite relay capabilities. Rural areas that rely on satellite internet would lose connectivity completely. Aviation systems would lose GPS navigation and satellite communication links that enable safe flight operations across oceanic routes. Maritime shipping would lose the satellite navigation systems necessary for efficient cargo delivery. Emergency response services would lose communication capabilities and GPS guidance systems that enable rapid response to disasters and medical emergencies. The permanent loss of orbital zones represents the destruction of infrastructure that required decades to develop and hundreds of billions of dollars to deploy. Satellite constellations like Starlink took years to design, manufacture, and launch into their operational orbits. GPS satellites provide navigation services that required massive government investment over multiple decades to achieve global coverage. Communication satellites enable international connectivity that transformed global commerce and social interaction. The orbital real estate that hosts these systems cannot be quickly replaced or easily relocated to alternative altitudes. International space agencies recognize the catastrophic potential of orbital debris cascades and coordinate efforts to prevent scenarios that could trigger Kessler Syndrome events. Space surveillance systems track thousands of debris objects to predict collision risks and enable satellite operators to perform avoidance maneuvers. Debris mitigation guidelines require satellite operators to plan for end-of-mission disposal to prevent spacecraft from becoming long-term debris hazards. The recognition of these catastrophic risks eventually forced world leaders to confront the terrifying implications of space nuclear testing and take decisive action to prevent future disasters. The treaties that ended space nuclear testing. The Limited Test Ban Treaty, signed August 5, 1963, banning nuclear tests in space, atmosphere, and underwater, marked the official end of humanity's brief and terrifying experiment with nuclear weapons in space. The United States and Soviet Union agreed to prohibit nuclear explosions in these environments after witnessing firsthand what space nuclear testing could do to the planet's electromagnetic environment. The treaty emerged directly from the chaos that Starfish Prime had created just 1 year earlier, when artificial radiation belts persisted far longer than anyone predicted, and satellite failures continued for months after the original explosion. The devastating effects of Starfish Prime influenced international nuclear testing agreements in ways that extend far beyond the immediate radiation and electromagnetic damage. Diplomatic cables from 1962 reveal that both superpowers recognized they had stumbled into territory where nuclear testing could create permanent changes to Earth's space environment that would affect all nations regardless of their participation in the testing programs. The artificial radiation belt created by the American space nuclear test posed ongoing threats to Soviet satellites and future space missions, demonstrating that space nuclear weapons couldn't be contained within national boundaries or targeted exclusively against enemy assets. International negotiators understood that space nuclear testing represented a fundamentally different category of weapons testing because the effects operated on planetary scales rather than regional ones. Unlike ground-based nuclear tests that created localized radioactive contamination, space nuclear explosions affected the global electromagnetic environment and orbital zones that all spacefaring nations would eventually need to use. The magnetic field connections that carried charged particles across hemispheres meant that space nuclear testing in one location could affect electronic systems anywhere on Earth, making traditional concepts of national sovereignty and territorial boundaries irrelevant. The treaty negotiations faced immediate urgency because both superpowers were planning additional space nuclear tests that could have created even more devastating artificial radiation effects. The Soviet Union had been developing its own space nuclear testing program in response to American electromagnetic weapon demonstrations, and military planners on both sides recognized that an unrestricted space nuclear arms race could render orbital zones permanently unusable for peaceful space exploration. The diplomatic pressure to prevent escalation overcame military desires to perfect electromagnetic warfare capabilities. The 1963 treaty established legal frameworks that prevent the testing of space-based nuclear weapons, creating international obligations that continue to influence space policy today. These agreements recognize that space nuclear testing poses unique threats to global infrastructure and environmental stability that transcend national boundaries. The treaty provisions specifically address the planetary-scale consequences of space nuclear explosions that affect all nations regardless of their participation in nuclear testing programs. Space agencies coordinate extensive efforts to prevent accidental electromagnetic interference that could replicate the effects of nuclear testing without using actual nuclear weapons. Solar storm monitoring systems track natural electromagnetic events that can disable satellites and disrupt communication networks in ways similar to artificial electromagnetic effects. International Space Weather Services provide warnings when solar activity threatens satellite operations. Ground control stations implement procedures to protect spacecraft during electromagnetic disturbances and restore functionality after electromagnetic damage occurs. The Comprehensive Nuclear Test Ban Treaty opened for signature in 1996, but has not entered into force because several key nations, including the United States, have not completed ratification. The treaty would ban all nuclear explosions, including the space nuclear testing that created artificial radiation belts during the 1960s. Russia revoked its ratification in November 2023, raising concerns about potential resumption of nuclear testing programs that could include space-based experiments. The incomplete international consensus on comprehensive nuclear testing bans leaves open the possibility that space nuclear testing could resume under different political circumstances. Modern space surveillance systems monitor orbital zones for signs of nuclear testing or electromagnetic weapon deployment that could violate existing treaties. Ground-based radar networks track satellites and space debris to detect unusual electromagnetic signatures that might indicate weapons testing. Space sensors monitor gamma-ray, X-ray emissions that would reveal nuclear explosions in space. International monitoring systems can detect electromagnetic anomalies that suggest directed energy weapon testing or accidental electromagnetic events that threaten satellite operations. Military space doctrine increasingly emphasizes defensive measures that protect satellite infrastructure from electromagnetic attacks without deploying space-based weapons that would violate international treaties. Satellite operators deploy radiation-hardened electronics that resist electromagnetic pulse effects. Communication networks include backup systems that maintain functionality during electromagnetic interference events. Critical satellites operate in orbital zones that avoid the artificial radiation belts created by 1960s nuclear testing. Space-based missile defense systems provide protection against anti-satellite weapons without deploying nuclear weapons in space. The legacy of 1960s space nuclear testing influences contemporary space policy through ongoing concerns about artificial radiation and electromagnetic warfare capabilities. Space agencies account for historical artificial radiation when planning new missions and designing spacecraft protection systems. Military planners recognize that electromagnetic weapons offer strategic advantages without the environmental consequences of nuclear testing. International space cooperation includes provisions for preventing electromagnetic interference and sharing space weather data that affects all spacefaring nations. The protective measures developed in response to space nuclear testing continue evolving as electromagnetic warfare technology advances and space infrastructure becomes more critical to modern civilization. Treaty frameworks established in the 1960s provide legal foundations for preventing space nuclear testing, but they require constant adaptation to address new electromagnetic threats that emerge as military technology develops. The international cooperation necessary to maintain peaceful space operations builds upon lessons learned from the artificial radiation and satellite failures that resulted from humanity's brief experiment with nuclear weapons in space. These treaty protections remain essential as space becomes increasingly crowded with commercial satellites and critical infrastructure that billions of people depend on daily. The decisions made in 1963 to ban space nuclear testing continue to shape the orbital environment that modern civilization relies upon for communication, navigation, and countless other services that define contemporary life. Today's space missions operate under design principles forged by nuclear catastrophe. Every satellite launched today operates in a space environment that was permanently altered by nuclear experiments from 60 years ago. The artificial radiation belts created by Starfish Prime have mostly dissipated, but their legacy lives on in the radiation-hardened electronics that protect modern spacecraft. Starfish Prime drove the 1963 treaty and forced lasting spacecraft design changes still relevant today. Space agencies still avoid orbits below 250 kilometers without disposal plans because of 1960s radiation belt lessons. They design missions around lessons learned from satellites that failed throughout the 1960s due to electromagnetic effects that scientists never predicted. The space debris tracking systems that protect our satellite networks exist because we learned that space nuclear testing creates consequences that persist for decades after the original explosions. LEO, safety, and future exploration depend on these Cold War-era lessons that transformed space from an experimental battlefield into the carefully managed orbital highway that modern civilization depends upon.